So my task is in fact a difficult one because I just want to introduce the subject and at the same time to put this relationship between the ocean and the atmosphere and the climate system in perspective, in a long-term perspective. And this is what I will try to do in a very simple-minded talk. I don't want to enter into too much details. So I will probably, this is maybe an offense, in fact, to the specialists, but I will try to also, again, repeat some of the basics about why the ocean is important in the climate system. When we think about the climate, immediately we think about the atmosphere, but clearly the climate is not only the atmosphere, it's also it's a complete system, complex system, and the ocean is a key component of it, which is exchanging energy, heat, stress with the wind, mechanic stress, and it is also exchanging water, which is very important also in the climatic system. So this is a key component, and this is just a schematic diagram summarizing, in fact, the climate system with the different components, which is not only the atmosphere. When we speak about the ocean, we have to remember that the ocean is not a pond. It is not static. It is very important, in fact, to acknowledge the fact that it is transporting heat. And when we consider, in fact, the radiative budget of the Earth, of the climate system, it's important, in fact, to remember that there is an excess when we plot, in fact, the incoming solar radiation minus, in fact, the albedo, the reflection. We have an excess, and when we compare this with the outgoing radiation, mainly infrared, from the Earth, there is an excess heat in the low latitudes and a deficit in the high latitude. So clearly, the mechanism that is compensating, that is transporting the net surplus to the high latitude is the convection within the climate system and the fluids, the envelopes around the Earth. So it's more or less like the story of a boiling pot where convection is transporting heat from the middle to the outer part of the pot. The climatic system is obviously much more complicated than this pot because it has the water can be found in different phases. We have water in the ocean. We have also ice at both ends, both sea ice, continental ice. We have also the atmosphere just above it, and one big complication is that the whole thing is heated not from below but from above, and one of the envelope is very transparent, the atmosphere. So it makes the whole thing complicated, but clearly the main important thing is that there is a net heat transport between the low latitude and the high latitude, and it amounts to about 6 petawatts, 10 to the 15 watts, around 14 north and 40 south, and we will come back to that later. So when the convection is not happening in a very simple case as in the boiling pot, it is more complicated, and at the surface, most of the heat transport is linked, in fact, to currents, and this is just a summary graph that is showing the main ocean currents. The surface ocean currents are, there is a typo here. They are organized in large gyres at the surface that are linked, in fact, to the wind stress. And because of the Coriolis force, in fact, the currents, the gyres, the transport is concentrated on western boundary of oceans as western boundary currents. But the big picture is more or less like this cartoon, which is caricatured, but this is giving us basically a good view about what is how the transport is organized at the broad scale. So, and each current, and especially the western boundary currents, receive names due to their speed, and but at the same time they belong, in fact, to a general system with more or less symmetry around the equator. So, and this wind-driven gyre circulation is superimposed on a deep sea circulation that is also organized at a global scale, and this is represented here. This is the cartoon. This is not a caricature, but this is a too highly simplified view of this large-scale meridional overturning circulation at the global scale. And so this is the very well-known Broker conveyor belt image, but at the same time, there is a reality in that thing, but the actual connection is a bit more complicated. So I took that from a recent paper by Marshall and Spear in 2012, where they summarized the knowledge that we have today about this organization of the large-scale circulation with a surface and subsurface of warm water transport, which is indicated in red, and the deep and bottom water circulation shown here in blue and green. What is important is to realize that, for example, in the Atlantic, there is a transport from south to north and sinking in regions that is localized in different regions of the North Atlantic, especially the Greenland, Iceland, Norwegian Sea here. There is also some sinking in the Labrador Sea, and then the whole thing is transported southward at depths. There is also a deep sea convection around Antarctica, especially in the Bering Sea and the Ross Sea, and upwelling is mainly organized in the Southern Ocean. This is the key feature of this new assessment of the global circulation. What is also important is that there is connection both in the deep but also at the surface. For example, we will speak later much about this warm route of transport between the Pacific, the Indian Ocean, and the Atlantic, which is happening at the southern tip of Africa. And we will come back later, especially also with the two last talks of the day with Mathieu Rouault and Arne Bierstosch, which is a very important region for the transport and the return of this circulation. As I said, the ocean are transporting heat. It's very important, and when we take into account atmospheric data and ocean data, it's possible, in fact, to draw and to study quantitatively, in fact, the transport of heat at the surface of the planet by the envelopes. And so, as a convention, there is the heat transport is counted positively when it moves northward. So this is a plot showing versus the latitude the heat transport that is realized both by the atmosphere and the ocean, with in petawatts, so 10 to the 15 watts. So the maximum is around 40 north and 40 south at about 6 petawatts. But when we break down, in fact, this transport, it's interesting to see what is the different components, especially most of the transport is linked to dry air in the atmosphere. There is also a very important component that is traditionally attributed, in fact, to the atmosphere, but which is linked, in fact, to the latent heat. But basically, the latent heat also belongs to the ocean because the water is evaporated at the surface of the ocean, and then the heat is given back to the atmosphere when water is precipitated. So this is the green curve that is showing, in fact, the component, for example, for the northern hemisphere, the components of transport linked to the latent heat. And there is also the ocean, which is a component that is very important in the heat transport, mainly in the low to mid latitude. And when we take the whole ocean as a mean, we can see that, for example, in the northern hemisphere, it transports about 2 petawatts at about 30 knots. And when we further break down, in fact, the study, it's interesting to compare the oceans. Obviously, there is a symmetry when we consider, in fact, the whole ocean. There is a symmetry around the equator, but for example, the Atlantic is not symmetric in terms of, does not show, in fact, the same symmetry around the equator as the other oceans. For example, the Atlantic, which is represented here as the dotted line, shows that there is northward transport everywhere from 50 south to the North Atlantic. So we can, when we take into account, in fact, the transport, it's we can summarize it like this graph, in fact. This is a graph showing the cross-section of temperature versus latitude. And basically, everything is more or less a transport at the surface and subsurface of something like 10 to the 6 cubic meter per second. 10 to the 6 cubic meter per second is called a sphere drop in oceanography. And this is warm water that is flowing from the south to the north, all the way from the southern hemisphere in the Atlantic. And it sinks at depth, as we mentioned it I mentioned it at the beginning, in different areas of the North Atlantic. And it loses heat, and then a southward flow is organized at about 2 to 3 kilometers, and we will speak much more about this during the later talk. And when we just take the accounting, we can calculate, in fact, the flux of heat that is transported, which is about 1 petawatt, as the more precise view was given to you before. So when we do a schematic diagram of what is happening in the North Atlantic, I showed that, that there are different locations where the water is sinking to the deep sea, but it's important also to realize that there are many processes that can affect, in fact, the sinking and the loss of buoyancy of the surface water, warm, salty current that loses temperature and then sinks in the deep sea. There are many parameters that can change in one direction or the other. Precipitation, heat flux, also snowfall, the river influx is important. Also the formation of sea ice is important for the brine formation and so forth. So we expect that if climate is changing, the ocean deep sea circulation will change. And the other way is also true. In fact, with changes of the heat transport, we can expect also much changes also above the atmosphere, in the atmosphere. It's possible, in fact, to follow this deep transport, especially in the North Atlantic, by looking at oceanography properties, such as classically the salinity distribution. So this is a cross-section showing, in fact, versus depth and latitude, the salinity, where we can see, in fact, this high salinity tongue that is corresponding, in fact, to the North Atlantic deep water. So this is a classical view, and we know that since the work of Wüst in the early 20th century. It's possible also to follow many other properties that show, in fact, the same kind of structure, showing this North Atlantic deep water flow. This is, for example, the oxygen content of the disordered oxygen in the North Atlantic. This is the cross-section, and basically the oxygen content, because of the temperature is low and the dissolution of oxygen is quite high in the sinking region, and then the oxygen gets consumed, in fact, by the bacterial respiration, by the remineralization of organic matter, and during the transport. And we can follow, in fact, basically the North Atlantic deep water also by looking at the oxygen content of seawater. And here there are, thousands of data that have been collected, in fact, to construct that diagram. It's also possible, in fact, in the oxygen there are some peculiarities, and we will see that in a minute. It's also important to remember that there are many other properties that are showing, in fact, this kind of static view of the North Atlantic deep water. It's possible also to look at other chemical properties, also isotopic properties, such as the carbon-13 to C12 ratio of dissolved CO2. I cite this because we will use that as a proxy, in fact, to study past changes. And there are many other properties that can be used, in fact, for proxies also of this North Atlantic deep water. The one way, these properties have changed slightly over the last few years. I spent some time during the teaching this year to show, in fact, the changes that have been experienced over the last decades. But a way to really see for a fact that there is a transport, it is easy, in fact, it is convenient, in fact, to look at what we call the transient traces that are moving, in fact, at depth. And it's very easy to do that, for example, with the tritium and the carbon-14, the bomb carbon-14 that was injected in the early 60s just after the nuclear bomb test in the atmosphere. And this is a view showing, in fact, the penetration of tritium in the North Atlantic. So this is a transect between Brazil and Canada versus depths at different time, 1981, 97, and 2003. And we can really see, in fact, the convection that is taking place and the transport by the North Atlantic deep water that is happening here. This is a way of really seeing it. And of course, when we try to go further, it's also possible to take into account those tracer data, in fact, to make calculation and to make inversion and to get the actual transport in terms of sphere drop. But it's also very convenient to see that there is transport for a fact. It's also possible to do that with the freons, the anthropogenic freons that have been injected also by the human activities. And this is a zoom over, that's a section in the Atlantic where we can see that the penetration of the freon is down to the bottom of the ocean in the North Atlantic, whereas the central Atlantic Ocean, this is very much like that also for the tritium and the bomb carbon-14. The depths of the deep Atlantic and the deep Pacific are not contaminated yet. It's because of the transport. The transport is mainly linked to advection and not pure diffusion. The other thing that is important to mention also as a transient tracer, it is directly the anthropogenic CO2, the dissolve that is dissolved in the deep ocean. And we have to remember that the deep ocean is really a sink that is quantitatively very important. It's stored about 1/3 of the injection of human CO2 since the beginning of the revolution, of the Industrial Revolution in the 19th century. And this is a plot, in fact, summarizing again the tracer data with hundreds and thousands of data over the North Atlantic, where we can see, in fact, the contamination of anthropogenic CO2, especially in the North Atlantic, which is due, in fact, to this sinking process. So the North Atlantic deep water formation and the deep circulation is very important, in fact, to sequester the CO2 in the deep ocean. So it means that the deep circulation in the Atlantic and also in other places as well. I mean, I did not quote here the Southern Ocean, the formation of the Antarctic intermediate waters that are also important, but clearly the deep circulation is a key component also for this sequestration of CO2, which means that if it is altered or changing through time, it can also alter and change the atmospheric pool, the concentration of CO2 in the atmosphere, and feedback on the climate. So all those are important facts, and the properties that I just showed you very rapidly and crudely are changing through time. For example, CO2 is, the anthropogenic CO2 is increasing through time in the deep ocean. The salinity, the temperature, the oxygen content of waters of surface and deep waters have changed slightly over the last decades, and we will see that over the full day of lectures. But at the same time, one of the problems with the instrumental data is that the time is very short, the time scale is very short, and the recent changes are quite subtle. And it's always difficult to distinguish those small changes from natural variability and to really identify large changes of climate and oceanography. So this is the reason why it's also interesting to turn to the past, looking at the past, in fact, to illustrate large changes of the ocean. And this is what I will try to do during the remaining part of the talk. So it will be quite simple, and I don't want to enter into the details. What I would like to do is to illustrate that over long time scales, ocean and climate were coupled. They are, and I don't want to enter into the mechanism, the precise mechanisms and the modeling that is associated to that. These are just examples of illustration that ocean and climate changes are coupled over the recent past of the Earth. So one good example of large change of climate is what is called the last glacial maximum. So this is a old in terms of, when we compare that to human life, but this is yesterday in terms of geology. This is the last glacial maximum. This is a picture of the northern hemisphere as it was with large ice sheets on the continent, for example, on Canada, in Scandinavia, and there were major changes at that time, 20,000 years before present, major changes of climate, especially sea level was down by more than 100 meters. There was much more sea ice. This is a very old picture, but this is still more or less valid to show it as a summary, and it is also unprecedented in terms of graphic quality. So I still use it. That's the original climate map, and there are a few errors here and there, but it's still convenient for illustration. So we can see here that is represented, in fact, the change, the isotherms, and also the change of the sea ice that was happening during the time period. And it's possible, in fact, with proxies, what we call paleoceanographic proxies, in fact, to go back, in fact, to reconstruct the physical and biological properties of the ocean of the past. So I don't have time, in fact, to really go into the details of what each proxy is that we use for reconstructing either qualitatively, semi-quantitatively, or even sometimes quantitatively the ocean of the past, but I just want to give you a few examples. So this is just a graph showing, for example, the sea ice change during the glacial period. This is the modern day seasonal cycle of the sea ice in the North Atlantic. We have the summer sea ice in September, in late September, and this is the mean for the summer, the winter sea ice maximum, and we can see that there is a large seasonal change. It's possible with by looking at sediments, and especially plankton, planktonic dinocysts, that are algae that are living in the in the surface layers, and it's possible when we find that in the sediments, and this is the work from De Vernal and Hilaire Marcel some time ago. It's possible, in fact, to reconstruct, in fact, to map the seasonal sea ice extent during that time period, when we select the level in the deep sea sediments that corresponds, that are dated to that time period. So this is a zoom of the western part of the Atlantic with Greenland. That's the Labrador Sea, the Quebec is here. And what it shows is basically that during the LGM, the last glacial maximum, the winter sea ice, now the summer sea ice extent that is shown here, the perennial sea ice cover, was more or less corresponding, in fact, to the winter sea ice of today. So there is a complete, very large change of extent of sea ice at that time, and the winter sea ice was occupying, in fact, a large chunk of the North Atlantic. So clearly, there was a large change of the sea ice during that time period. So that's just a picture of fractured sea ice in the North Atlantic. It's also possible to go in the southern hemisphere to look at the sea ice distribution with other type of organisms. I took that from the work by Gersonde et al. From the Alfred Wegener Institute, where they reconstructed, in fact, the extent of sea ice during the LGM by looking at diatoms in sediments and also by looking at radiolaria. And this is the comparison of the extent of the winter sea ice of today, and this is the extent during that time period. So clearly, when we take into account the surface, there is basically a doubling of the sea ice extent during that time period. It's also possible, in fact, to look at some details of the oceanography of the past by looking at sediments that are collected in key locations. So this is there are hundreds of examples in the literature in paleoceanography. I just take one key example because I talked about this warm route of return flow for the global meridional overturning circulation at the southern tip of Africa. And this is a bit of some context about it. We will hear two more accurate pictures and talks about it this afternoon. But this is just a very broad and crude summary of what is happening there. There is a a western boundary current, the Agulhas current that flows south, and when it basically collides, in fact, with the eastward flowing currents that are, I mean, south we have the ACC, the Antarctic Circumpolar Current. When it collides, in fact, with the eastward flowing currents, it turns back. We call that the Agulhas retroflexion, and then the Agulhas current moves as the Agulhas return current eastward with meanders. I mean, this area is very dynamic, and we can see that with the variability of the dynamic height with satellites. So this is a picture, in fact, showing, in fact, the variability of the dynamic height based on satellite data in centimeters. So we can see that there is a large variability corresponding, in fact, to this area. It's also possible, I mean, the water masses at the surface here are more or less devoid of nutrients, whereas in the Southern Ocean we have a lot of nutrients due to upwelling. So clearly this is the reason why when we look at the chlorophyll based on the color of the ocean, it's possible, in fact, to see for a fact the meanders of the... So that's a picture showing, in fact, the chlorophyll based on the color zone coastal scanner with high productivity in the southern part of the diagram, in the southern latitude, which is due to upwelling of nutrients. So we can see that as a high concentration of nutrients and then chlorophyll, and we can even see the meanders that are very evident on that picture. What is also very important is that the Agulhas retroflections turns into the back, in fact, into the Indian Ocean, but there is a leak, in fact. Some of the water is leaking in the North Atlantic. It's not a steady flow, but this is actually made as eddies, energetic eddies and rings that are giving, in fact, salt and heat to the Atlantic. So this is a very key component of the global circulation at the surface and depths. And obviously, this Agulhas retroflexion and return current is very sensitive, in fact, to the position of the wind above it and the position of the subtropical front. And any movement north or south of this frontal zone will affect, in fact, this oceanographic feature and the leak of salt and heat into the Atlantic. So in order to study that broadly on very long time scale, we studied, in fact, different sediment cores, and I will just show two examples. One core that was collected on the Indian Ocean side of the prime, and the other deep sea sediment core that was collected by German colleagues on the eastern part, on the western part, on the Atlantic part of the graphic. This is a graph that is showing, in fact, what we reconstructed versus time. So I don't have time to explain in details what we are doing, but basically we have a deep sea sediment core. We measure different proxies as mainly, in that case, geochemical tools that allows us to go back, in fact, to temperatures, for example, to sea surface temperature or to productivity. And we plot that because we have also other techniques, in fact, to date the sediment. We can go back through time and plot those as time series. So this is a graphic that is summarizing, in fact, the key information that was obtained from that deep sea sediment core that was collected in the Agulhas currents region, but in the Indian Ocean sector versus time. And here we can see the last 800,000 of years, so almost the last millennia. And when we plot, in fact, the ages in BP, in that case, the modern period is at 0. On all my graph, I will show, in fact, an arrow that is showing the progression of time, because sometimes it is the other way around, depending on the convention of the authors. What can be seen here is that we can catch with the proxies that we measure for temperatures. For example, we measure some specific organic compounds that tell us, in fact, the sea surface temperature of the time. We can see large changes of the temperature that are corresponding, in fact, to glacial, interglacial changes. But superimposed on that, we can see also that there are specific glacial maxima that were much colder than what we expected before. And they do correspond, in fact, to large changes of the productivity and also to large changes of a proxy that we use as an indicator for the connection between the deep Atlantic and the deep Pacific, which is the gradient of the carbon-13 to C12 ratio in the benthic foraminifera. So when I presented at the beginning the graph showing the oxygen content of the deep water, I said to you that there is a correlation also with C13 of dissolved carbon. And this is what we use, in fact, to reconstruct the oxygen content and also the overturning strength in terms of qualitative words. And basically what we can identify with that is that during those time periods, during these specific glacial maxima, the leakage from the Indian Ocean was more or less stopped, in fact. And this is probably the reason why, because it has an effect on the Atlantic circulation, and then on heat transport. This is the reason why we think that those cold periods, those glacial maxima, were even colder than expected from what we see from the others. It's possible also to look at the other deep sea sediment core that is on the Atlantic side, and this was done by a team of colleagues from Germany and Spain. And this is again a graph that is showing versus age. The 0 is here. We have different glacial periods that are identified based on temperature proxies, but it's possible also the colleagues did the counting of fossil foraminifera that are typical from the Indian Ocean. They call that the tropical, subtropical Agulhas leakage fauna. And usually this fauna of foraminifera, that's just an example, STM picture of it, is confined to the Indian Ocean side, but there is a large variability through time, and especially during the glacial period, there is a collapse of this leakage fauna, which indicates to us that the leakage of the Agulhas was much lower during the glacial periods, and as I showed you, there were even some periods when basically it was more or less shut down. There are other periods when it's possible to identify, in fact, large changes of the ocean-atmosphere couple, and on more recent periods. And it's a very classical example are the hydrological perturbations that are linked to collapses of the main ice sheet that was located in North America at the time of the glacial period. So here we'll speak mainly about the last glacial period. From time to time, it's not periodic, the Laurentide ice sheet was losing parts of its mass as icebergs, and these icebergs, we can see them in the sediment because they were transporting what we call ice-rafted debris. This is a picture of these ice-rafted debris under the binocular. So it's possible to identify them in the sediment. And we have there are hundreds of examples of records in the North Atlantic of climate and deep ocean proxies. I'm just showing here a graphic that is showing one example of North Atlantic record for the last 100,000 years. In that case, it is only the last glacial period. Previously, I was showing many glacial periods over 1 million of years. Here, it is only the last 100,000. Here, you have the 0, so the modern period. And what we can see is that, so this is the modern period, what we call the Holocene, and during the glacial period, there were large swings, large changes, in fact, in the intensity of the deep Atlantic circulation. We can see that with very conveniently in one of the cores. So I'm showing the results that were obtained in one particular core in the North Atlantic. I could have shown many others. I could also plot other proxies for the intensity, the qualitative intensity of the deep Atlantic circulation. In that case, what I used for convenience is the C13 to C12 ratio in benthic foraminifera. So we can see large swings. And I could have shown you other proxies that would basically look the same at that scale. What is important is that each time that we had a massive injection of meltwater that are indicated as with the gray bar, they are corresponding to what we call the Henrik events, there was a collapse basically of the deep sea circulation in the Atlantic, and because of the heat transport that we saw at the beginning in the North Atlantic, it had a dramatic effect on the North Atlantic temperature, so the sea surface temperature. We can see that here. We can see that each time that there was a drop in in the deep sea circulation, there was a big drop in the North Atlantic sea surface temperature, but not only because of the heat transport that is so important for the atmosphere. We can see that also as very large changes, for example, in Greenland air temperature that is measured with the oxygen 18 to 016 ratio of seawater. It's also possible to go, so this was the case for the North Atlantic. There are also many other examples in the literature of changes over the same time scale, not so much with sea surface temperature, but with other properties. The hydrological cycle also was very much affected in other parts of the planet over the same time scale. And it's important also to look at other properties. So I'm just showing to you here an example of another sediment study over the same time scale, but at the complete other end of the deep sea circulation, the dead ends of the northern Indian Ocean. And I could have shown you also examples of the eastern part of the Pacific Ocean. I won't have time to do that today, but this is just an example of what we are doing, for example, in the northern Indian Ocean. So these graphs are just to show you that the Arabian Sea, and to remind you that in that part of the world, there is, so deep sea circulation is, I mean, the deep water masses are quite old and aged because they have to go all the way from the Southern Ocean to the north. I mean, actually the oceanography is quite more complicated than that, but superimposed on that, we have also the productivity, which is linked, in fact, to the monsoon changes. We can see that, for example, from satellite data for the modern day. This is the summer monsoon upwelling, which is showing a large productivity based on the chlorophyll content, based on satellite data. This is the northeast monsoon that is showing also large mixing and bringing up nutrients at the surface. The Arabian Sea is a very particular location that is very sensitive, in fact, to changes of the Asian monsoon and the ocean circulation. That's a cartoon, so this is the north and the south, that is summarizing, in fact, the processes that can change. So this is highly schematic, but we can have winds, we can have wind-blown dust, we can have river input, and the whole thing, and also nutrients input at the surface linked to the upwelling, and also the oxygen content that is modulated by the deep and intermediate circulation. This is affecting, in fact, the remineralization of the organic matter that falls down from the surface. So this is the simple equation of the primary production based on photosynthesis, so formation of carbohydrate. This organic matter sinks at depth and is degraded by bacteria. The bacteria are consuming, in fact, the oxygen, the dissolved oxygen, and when the dissolved oxygen is almost zero, they can switch, in fact, other type of bacteria are using the nitrate, the dissolved nitrate, and do denitrification. And in that case, they produce gases such as nitrous oxide, and they can go down, in fact, even to nitrogen. But this is, and we, in order to study those processes, we looked at different sediment cores. So this is, again, a graph showing versus depth the modern data of oxygen. Here, this is the oxygen saturation versus depth. And we collected different cores within and below this so-called oxygen minimum zone. And what is quite interesting, in fact, is by looking at those well-dated sediments, it's possible to see wide changes of the denitrification and of the oxygenation at depth. So these are graphs that are shown, in fact, here versus time, again. 0 is modern day period, 50,000 years. We can see with a proxy, we use, in fact, the delta N15, the 15 to 14N isotopic ratio as a proxy for the denitrification. High values indicate that the OMZ, the oxygen minimum zone, was very intense. And when we add minima of this delta N15, it means that the oxygen minimum zone was almost absent. The intermediate depths of the northern Indian Ocean were fully oxygenated. There was no denitrification. And we can see that also, and this is just to illustrate how large the changes can be. In fact, we can see that even on the biodiversity of the organisms of the benthos. So this is an index of the biodiversity of the benthic forams. This is taken from a work that we are conducting in my group with Laetitia Licari at CEREGE in Aix, and she, in fact, counted, the numbers of benthic foraminifera and showed that, obviously, it increased very much when the oxygen was replenished, when the OMZ was almost absent. And it's also possible to have the mirror image of the whole thing by counting only the species that are adapted to oxygen deficit, and we can see that there is a correlation, a very nice correlation between this percentage of species adapted to oxygen deficit and the intensity of the denitrification. So this is the kind of thing that we can do with paleoceanography, just to illustrate how large the changes can be over those time periods. We can also zoom at the last deglaciation, which is the part of the record that is changing the most. I mean, I forgot to mention also that is quite important, that it's also interesting to compare the delta N15 variability over the same time scale as what the glaciologists are measuring in the bubbles of the ice cores in Antarctica and Greenland. It's possible to measure the concentration of atmospheric N2O, and here the graphic could be updated because there are even more data today, but clearly what we see in the Indian Ocean, the denitrification proxy, is corresponding point by point. I mean, here it's very clear that there is a very nice correlation. Of course, it doesn't mean that the N2O content of the atmosphere is only driven by the Arabian Sea denitrification, but because other oxygen minimum zones, especially in the eastern Pacific, are behaving like that, it means that collectively, probably part of the reason for this variability is linked to the intensity of the denitrification that is changing due ultimately to what is happening in the North Atlantic and those icebergs. So clearly the teleconnections are quite large. I said to you that it's possible to look at the deglaciation, and I would like to concentrate on this over the last few minutes of my talk. It's interesting to look at the deglaciation not only at specific sites, but also by looking and compiling different well-dated temperature records. So this is something that we did recently under the leadership of Jeremy Shakun, who was at that time at Oregon State University, now is at Harvard, and in collaboration with a team of colleagues from the US. This is just showing, in fact, the well-dated cores and records that we compiled. A significant part of the complexity of this compilation is linked to the synchronization of the different records. I have no time to enter into those details, just to show you it as a philatelic slide. I'm showing here, in fact, the 80 records versus time that have been synchronized. So here, each stamp here is showing one of the records versus time with the error bar on the sea surface temperature, mainly because these are mainly ocean sites. So this is the records that we compiled and that we checked and calibrated. When we do that, it's quite interesting because when we compile and make a global curve, because that was the intention to get at the global temperature over the full deglaciation, it's possible to plot that versus, for example, the Antarctica temperature based on the ice core. But it's also possible to show that most of the global deglacial warming, in fact, is lagging the CO2 rise. So that's a separate prime, but many people have been caricaturing, in fact, the prime of lead lag of over the last deglaciation. Clearly, what we can see here is that the global temperature is lagging the CO2 warming, which is not, in fact, the driving force, the pacemaker of the deglaciation. We know that glacial periods are linked ultimately to Milankovitch and orbital cycles, and that are probably giving the small notch at the beginning. But clearly the CO2 is an important feedback, and we can see that over most of the deglaciation, the global temperature is lagging. It's even more important for what I want to tell you about the ocean to consider different latitudinal bands. So this is the deglacial warming at different latitudinal bands. We can see, starting from the southern hemisphere, we can see that the southern hemisphere is leading, in fact, the northern hemisphere that are shown here. Here you have the latitudinal band between 30 and 60, between 60 and 90. They are all delayed. There is probably also a small rise of temperature at the beginning, but clearly the 30 to 60 north latitudinal band is lagging, and there is even a reversal. So this reversal is quite interesting. In fact, we can even plot on the same time scales, again, make a mean over for the temperature record for the southern hemisphere. This is shown here as the red curve. This is the southern hemisphere temperature. Here we have the northern hemisphere temperature by collecting all the data from the northern hemisphere. And it's interesting to plot that versus the CO2 curve in the atmosphere based on the bubble data to show again that the southern, for example, the northern hemisphere is definitely lagging the CO2 curve. Probably the southern hemisphere is increasing before because, again, this is probably there are other forcings that are starting the process. But what is very interesting is to make the gradient between the southern hemisphere and the northern hemisphere. This is the north-south delta T that is shown here globally. And it's even more interesting to plot that only for the Atlantic. This is the north-south Atlantic delta T. And we can compare that to a first order with, I could have plotted a C13 curve here in the paper. What we used is a classical order proxy that is used as a proxy for the intensity of the Atlantic meridional overturning circulation, which is the protactinium-thorium ratio. And we can see that there is a quite close correspondence. So very probably this delay and this reversal even of the temperature record over the last glaciation for the northern hemisphere is purely linked to the ocean response. During Henrik I and during what we call the Younger Dryas period, we can see that with the correlation. So the paper is much more complicated. The paper that we did with Shakun et al. Is much more complicated because we have a significant part of modeling with the ocean atmosphere GCM based on, I mean, it's mainly the work of the NCAR team in Boulder, but this is, the big picture of it is underlining the important role of the ocean for this glacial to interglacial rise of temperature and the delay that is produced, in fact, by the ocean circulation, mainly the Atlantic circulation of the ocean in the Atlantic. So that's a paper which should be published at the end of next week. So I promised to you to finish with some simple-minded thoughts. Very simple because Paleoceanography is not doing everything quantitatively, and we have a full day of lectures that will teach us a lot of the more complex stories about the recent past. But Paleoceanography is a good tool, at least to teach us, to tell us that the ocean is clearly a key player in the climate system. It can moderate by smoothing and delaying the response to climate, to the atmospheric perturbations, but not only. It can also either amplify. We have seen that with the Agulhas retroflexion and the leakage between the Indian Ocean and the Atlantic. And we can see also, for example, during the last deglaciation, that it can curb, it can reverse, in fact, the direction, at least on a transient basis, of the large climatic changes that are happening at the scale of the planet. So it creates positive and negative feedbacks. Thanks a lot for your attention.